Ladies and gentlemen, here we have another problem on induction motors. So, 40 horsepower, 1760 RPM for 40 volts, three-phase squirrel cage induction motor is made to operate as an asynchronous generator. The rated current of the motor is 41 amps and the full load power factor is 0.84. So we are told that we need to calculate the capacitance required per phase if the capacitors are connected in a delta configuration. And at what speed should the driving engine run to generate a frequency of 60 Hz? So let's right away begin and let's understand this problem. Now we are told that we have an induction motor, but we want it to operate as a synchronous generator. So when it is to operate as a synchronous generator, we must get a prime mover that is going to move faster or ahead of the synchronous speed of the rotating magnetic field of the stator. Now, the rated current of the motor is that, the load power factor is this. So, what is going to be the capacitance required per phase if the capacitors are to be connected in delta configuration? So, first of all, we need to look at the total power, apparent power. So the apparent power that we can always call S is actually equal to root of 3, since this is a three-phase system, times V times I. So I know this is root 3 times the voltage, which is 440, times I, which is 41. So what is this going to give us? Root 3 times 440 times 41. So we are getting S equivalent to 31,246.1966. So this is in volt amperes. So this is the apparent power, so it must be in volt amperes. So if we want the true power, but of course remember, according to the power triangle, the apparent gives us the true and the reactive. So true power, let me say true power is equal to, it's going to be S times cos phi. And this is 31,246.1966 times 0.84. So if I multiply by 0.84, I get 26,246.8051, and this is in watts. So since this is the active power, it is measured in watts. So what happens after getting the true power? We need to get the true reactive power, because it is this true reactive power that gives us, that tells us how much of the capacitance is required. So this is going to be S, obviously is going to be S squared minus the true power, 26,246.8051 squared, and everything under root. Remember, this is coming from this triangle. If I have S, I have 2, and I have true power, then for me to get this 2, I can say this is S squared minus T squared, everything under root. So What is the true reactive? I'm going to be having true as 31,246.1966 squared minus 2646 2646 246 then 0.8051 squared. Remember, this is under root. So true reactive is actually becoming 16,953.76. 1, this is in volt ampere reactive. So remember, this is the total for the whole bank. So if I want true per phase, remember I have 3 phases, so it will be this true total divided by 3. So this is 16,953.761 divided by 3. And true is actually equal to 5651.254 volt amperes. Now, what do I do with this value? I can choose to directly relate this with, if I have this true, I can as well say this is the same as having IC, the current through the capacitance, then, or the current across just one capacitor, I multiply it by Vc times sine phi. But phi is equal to 90 for a capacitor. So what does that mean? I can get IC, which is 2 divided by Vc. And this is going to be what? It's going to be, remember, this is delta connected. So delta connected, the phase voltage is the same as line voltage. So this is going to be 5651.254, okay, divided by 440. So divided by 440, I'll get the current as 12.844 amps. So if I get current as that, I can as well say that the voltage across that one capacitor is IC times XC, whereby XC is the capacitive reactance. So this capacitive reactance therefore will be 440 divided by 12.844. So 440 divided by 12.844. So we are getting this is 30 to 34.26, and this is in ohms. So but we know that XC, capacitive reactance, is the same as omega 1 out of omega C, meaning that I can get C as 1 out of XC times omega, meaning that C can be 1 out of 34.26 times 2 pi times F, which is 50. So times 100 pi, so 1 divided by this value, and I'm getting C equal to 92.9 2 times 10 to the power negative 6 Faradays. So the capacitance of the capacitor required per phase will be 92.92 microfarads. So at what speed should the driving engine run to generate a frequency of 60? So here, for it to generate, so we are going to part B. So for the induction motor act as asynchronous generator, it must be driven faster than the synchronous speed of the rotating magnetic field. So what does that call us to look for? We already know that the speed is 1760 RPM, so we can get NS. NS is 120 F divided by P, and this is going to be 120 times 50 divided by P. The P is the number of poles, and the number of poles are the number of poles are not given, but we can see that the nearest speed is 1800. So if the nearest speed is 1800, so how many poles are this going to be? Remember, actually this is supposed to be 60. So divided by P, for us to get 18 here, what is this going to be? So 12, 0 times 600 times 60, we are going to divide it by, so if we divide it by 4 poles, this is going to be 1800 RPM. So meaning we can get slip. So the slip is going to be NS minus NR divided by NR. So this is 1800 minus 1760. This is divided by NS. So 18 minus 1760 divided by 1800. Okay, even if I don't do so this gives us slip as 0.02, but of course this is going to be as that, and then this would be 2%. Now let us take just the slip NS, or what we are calling the slip speed, that will be 1800 minus 1760, and this is 40 RPM. So the speed is going to be slightly higher. So we know that the speed is slightly higher than the synchronous speed. So if the synchronous speed is 18, it will be slightly higher than the same slip when it is acting as a motor. So it will be 40, and this is going to be 1840 RPM. So this is the speed that the speed with which the asynchronous generator is going to be operating when it is to generate power at a frequency of 60 Hz. So that's it.